In this video, we are going to discuss the depth first search or the DFS traversal. Traversal, as we know, is the process of visiting each vertex in a graph, and each vertex should be visited only once. The depth first search, it starts at some selected vertex, which is also known as the source or the starting vertex. So it could be any vertex of this graph depending upon your choice. It could be 0, 1, 2, 3, 4. And then for that particular node, we have to go into the depth. That means visit as far as possible along each branch. So we have to go deep, and once we reach any node for which we cannot go further deep, then we have to start backtracking. In this traversal, we are going to implement using a stack, and stack we know is a LIFO data structure, which is last in first out. So we will visit an adjacent unvisited node. So starting from one node, we will visit an unvisited node in its neighborhood. We will mark that node as visited and push it into the stack, and we will keep on doing these two steps, and if no adjacent unvisited vertex is found, then we are going to pop up the vertex from the stack for backtracking. We are going to look into this in more detail. Also, since graphs may contain cycles, there is a possibility that we may come to the same vertex again. So to make sure that each vertex is visited only once, we are going to mark these nodes as visited or not visited. So this is one example that we are going to take. This example, as you can see, this graph has 9 nodes, and we are going to take a stack which is initially empty. We are going to pick one starting node. It could be any node in this graph. We are starting, in our example, we are starting with node 0. We will push this node 0 onto the stack. So this is the top of the stack, just pointing to the topmost element in the stack. Also, we can print 0. Now we have to explore the unvisited neighbors of 0. So if you check the neighbors of 0, it is 1 and 3. Both are unvisited currently, and we can pick any of these neighbors. So let's say we have picked up 1. So from 0, we are going to 1. So we will push 1 onto the stack. Also, we can print 1, and the top of the stack is now pointing to 1. From 1, so whichever was the element at the top of the stack, we are going to check its unvisited neighbors. So since currently 1 is on the top of the stack, we will check its neighbors. Its neighbors are 0 and 2, but 0 was already visited. The only unvisited neighbor is 2. So we are going to push 2 also on the stack, printed. Top of the stack points to 2. Since 2 is at the top of the stack, we will visit neighbors of 2. If you check the unvisited neighbors of 2, if we check from this, the unvisited neighbors of 2 are 3 and 4. So we can pick any, and here in this case we have picked 3, so we have put 3 on top of the stack now. We are simultaneously we can print it also. Also, now if you check the neighbors of unvisited neighbors of 3, we find that there are no unvisited neighbors. All these neighbors have been visited. 0 has been visited, 2 has also been visited. So now we have to do a backtracking step. So what we are going to do is, from 3, now we are going to backtrack to 2, and this is done by removing 3 from the top of the stack. So we do a backtrack, and now we have reached 2, which was from where we started before we came to 3. Now again from 2, we will check its unvisited neighbors. So let's check the unvisited neighbor. It is 4. So from 2, we have moved to 4 and put it on the top of the stack, and also put it in the print. From 4 again we can check its unvisited neighbors. If we check the unvisited neighbors of 4, it's 5, 6, 7 and 8. All of these are unvisited and we can pick any of these. So here in our example we have picked 7 and we have pushed 7 on the stack. Now when we will explore unvisited neighbors of 7, there is no unvisited neighbor. 4 is the only neighbor and 4 has already been visited. So at this point now we have to backtrack. So we will go back to 4 and this backtracking we do by popping 7 out of the stack. So we pop out 7 out of the stack and go back to 4 over here. Now the neighbors of 4, unvisited neighbors are 5, 6 and 8 and we can choose any of these 3 unvisited neighbors. Let's say we have picked 5. So we have picked 5, we put it onto the stack. We have got it printed also over here. And now on reaching 5, again we will see the unvisited neighbors of 5. We see that the unvisited neighbor of 5 is only 6. So we will push 6 also on top of the stack. Now when we reach 6, we see that there is no unvisited neighbor. That means we have to backtrack. And for backtracking, that means we have to pop out 6 from the stack and go back to 5. So here we have gone back to 5. So 5 is on top of the stack. Now again we check the unvisited neighbors of 5. Again we find that there is no unvisited neighbor of 5. So that means we have to do further backtracking and pop out 5 also and go back to 4. So now we have gone back to 4 over here and now we check unvisited neighbors of 4. So we see that the unvisited neighbor of 4 is 8. So we can now go to 8 from 4, put it on top of the stack. After reaching 8, now we find unvisited neighbors of 8. We find that there is no unvisited neighbor of 8. So that means we have to backtrack by removing 8 from the stack. So we pop out 8 from the stack and reach 4. Again, there are no unvisited neighbors of 4. So we have to backtrack again, remove 4 from the top of the stack and now we are left with from where we started going into the depth. That means we started from node 2 to 4. So we have to go back to node 2. So here we are back in node 2, checking unvisited neighbors of 2 again. There are none. We have to backtrack and that means we have to go to node 1. We go to node 1. There are no unvisited neighbors. We backtrack by popping out 1 from the stack and go back to its node from where we started and we are in on node 0. Again we have to check unvisited neighbors of 0. There are none, so we have to backtrack again, which is, so we pop out 0, but now we are left with an empty stack. So this is what the depth first search algorithm is, and we can have any traversal that we can start with any node. We can go to any other unvisited node. So this is not unique. You can have multiple sequences generated out of this. The time complexity of this algorithm is of the order of V plus E, where V is the number of nodes or vertices and E is the number of edges. This depth first search algorithm can be used for searching for connected components, detecting cycles in graph, topological sorting and finding bridges in the graph. We will cover all of these in subsequent lectures. Now we will take a look at the pseudocode of this DFS algorithm. So we have a graph G and a starting node V. And we are going to take the same example that we did earlier. So we take a stack which is initially empty. So this is our stack S. And for each vertex U in VG, so VG is the array of vertices of the graph, and all these vertices, for all these vertices we are going to mark their visited as false. So here we are creating an array, and for all these vertices we are going to mark them as unvisited. So false means unvisited. So visited u, false means that this node u is unvisited currently. So first we are going to push the starting node onto the stack. So we have, since in this example we took 0 as our starting node, we are going to push 0 onto our stack and we are going to mark it as visited. So 0 has been marked as visited because visited v is equal to true. Now till the time the stack is not empty, we are going to do all these steps. First we are going to pop the stack and put that into u. So if we pop out the stack, so u becomes 0 and we have popped it out, so we can have it printed also. So 0 is no longer onto the stack, and for each unvisited neighbor w of u, we are going to push it onto the stack and we are going to mark it as visited. So let's check unvisited neighbors of u. We have two neighbors, 1 and 3. So we will push them onto the stack, 1 and 3. It could be in any order, 1 or 3 or 1, and we will mark them as visited. So 1 is also visited and 3 is also visited. Now we go back to our while loop. Stack is not empty, so we pop out from the stack. So now what we pop out is 3. So we pop out 3, so 3 is no longer there. We can get it printed also. And now we are going to check unvisited neighbors of 3. So unvisited neighbor of 3 is only 2, which we are going to put onto the stack and also mark it as visited. Now in our next iteration, our u becomes 2 because it will be popped out, no longer on the stack, and now we have to push the unvisited neighbors of 2 onto the stack, and unvisited neighbor of 2 is only 4. So 4 goes onto the stack and 4 is also marked as visited. In our next iteration, u becomes 4. So 4 is being popped out. It has been popped out of the stack, and now we have to check unvisited neighbors of 4. We check our unvisited neighbors of 4. We have 5, 6, 7 and 8, which we are going to push onto the stack, 5, 6, 7 and 8. In the next iteration, we are going to pop the stack, so our u becomes 8 and we are going to get it printed. So 8 we have marked all of these as visited also when we push them onto the stack. So 8 has been marked as visited, and now when we pop it out, we check unvisited neighbors of 8. There are none. So then again we go back to our next iteration and pop out from the stack again, so which is 7. So now this is 7. Again we check unvisited neighbors of 7. There are none. So we go back to our while loop, pop out again. So 6 is also popped out and we can get it printed. Again there are no unvisited neighbors of 6. We go start again. Our u is now 5, which gets out from the stack. There are no unvisited neighbors of 5 because all have been marked as visited. We go back to our while loop and pop out again, and now we are back to 1. There are no unvisited neighbors of 1, and now our stack is empty. So this is the sequence, this is the depth first search sequence that we have got. Let us see that using our logic that we did earlier, the example that we did earlier, is this correct or not? We can start this again. So we started with node 0. Now we are going to check this particular sequence. We started with 0. We have to go to one unvisited node, which we went to 3. So we are at 3. And mind you, we have to go in deep. We have to go depth wise. So we have to go from one node, we have to go into the depth of that particular node. Unlike breadth first, where we cover all the immediate neighbors first. Here we will go into the deep of one branch only. So from 3, unvisited neighbor is 2. So we can go to 2. From 2, unvisited neighbors are 1 and 4. We can pick any. So we have picked 4. So now we have reached 4 over here. From 4 we can choose between 5, 6, 8 and 7. We have chosen 8. So let's go here. At 8 there are no unvisited neighbors. So we have to do a backtrack and reach node 4 again. From 4 again we can check unvisited neighbors. We have gone to 7. So we are at 7. 7 does not have any unvisited neighbor. So we backtrack again, reach node 4 again, check unvisited neighbors of 4. We have chosen 6. So we go to 6. 6 has one unvisited neighbor which is 5. So we can go to 5. From 5 there are no unvisited neighbor. So we go back to 6. Go back to 4. No unvisited neighbor of 4. So we backtrack to 2. Now 2 has one unvisited neighbor, 1. So we print 1. So we have seen how this depth first search algorithm works.